Right, it is my very great pleasure to welcome Professor Sarah Rees from Newcastle UK, who has agreed to make a little stopover at Penrith on her way to Newcastle, Australia for the conference. And she's going to tell us about Artin groups, in particular when Artin groups are sufficiently large. Thanks.
Thanks very much, Volker. It's really a pleasure to be here. I hope I'm looking in the right direction. It's great to be here, and the weather's terrific too. So, I'm going to talk about Artin groups, particularly big Artin groups, for which an awful lot of things are possible. So what am I going to do? Oh yes, okay. So I'm talking about joint work. So all of this work is joint with Derek Holt. Some of it is joint with Laura Jabanu, and some of it is, which I don't mention very much, is with Eddie Goodell. So I'm talking about sufficiently large Artin groups. So they're Artin groups that belong to the same family of groups as braid groups, but they're different. A lot of the same things are true about them, but the things that are true about them you see in different ways. Okay, so for these groups, the first contact with these groups was with my joint work with Derek, where we discovered that we could describe the geodesics in these groups very easily, and in particular the short lex geodesics as well. And we found a rewrite system that allowed us to very quickly reduce words in these generators of these groups, and the standard generators of these groups, into short lex geodesic normal form. And once we knew how to do that, we could solve a lot of problems in the groups. We could solve the word problem, we proved short lex automaticity, and we could solve the conjugacy problem for some of these groups in cubic time. Well, we used an algorithm due to Apple and Shook, but we could prove that this algorithm worked very quickly. We could derive the rapid decay property, this work with Laura, for many of these groups, including all the extra large type groups, and so we were able to prove that the Baum-Kohn conjecture holds for these groups. And then I talked to Eddie Goodell, and we discovered that we can prove a kind of weak form of hyperbolicity, which he had already proved for the spherical type and other Artin groups. We could derive that too for our sufficiently large groups. Okay, so there's a number of different problems I'm talking about, whose solution is based on the fact that we could rewrite these groups into this normal form, the short lex minimal geodesics. Okay, so there's a lot of different things I have to talk about, and so what am I going to do? First of all, I'll talk to you about the types of problems we were solving for groups in general. Okay, I'll explain to you what I mean by a word, a geodesic normal form in a group. I'll explain what it means for a group to be short lex automatic. I'll talk about the rapid decay property and the Baum-Kohn conjecture and the relationship between all of these. Okay, so that's for groups in general. Then I'm going to go on to Artin groups, so I'm going to say what an Artin group is, and give you a bit of historical background about what is known about Artin groups and what isn't. Okay, and then I'm going to talk about our work in particular. So about Artin groups of sufficiently large type. I'll give you some details on how we did all of this. And I'm sure I won't get through all of it, or I won't without speaking extremely fast, and then nobody will understand me. So if I do speak too fast, I hope somebody will interrupt.
I think we'll get kicked out at 3. Until then, you have time as far as I'm concerned.
Yeah, but when I speak too fast, it's a waste of time, so you should slow me down. But as I relax, I might slow down a bit. Anyway, here we are. So we're going to start by introducing the problems, okay? And I'm going to try and look at you and not at that camera, which is a bit impersonal. Okay, so where are we? Okay, so we've got a group. The group is called G, and it's got a finite generating set, which is called X. And so the elements in G are represented by words over X, and these are strings of symbols from X together with its set of inverses, okay? So a word is an element of the set x plus minus star, where x plus minus is the union of X with its set of inverses, the union of the set of generators and the set of inverses of generators, okay? Words are strings over that set, and a word has length, which is the number of elements in it when it's written as a string, and that is the symbol I use for representing the length of a string. And a word is geodesic if it is no longer than any other word that represents the same group element. Okay? So a word is a geodesic, as an element of the group. So if I've got an order on the set consisting of the elements and its of the generators and their inverses, so an order on the alphabet over which the words are written as strings, then I can compare two words in the short lex word order, okay? So when I have two words, W, U and V, then U is less than V in the short lex word order if either it's shorter than it as a string, or they have the same length, but in the dictionary, then U appears earlier than V does, right? So in a dictionary, man appears earlier than men, and it's the same length in it as it. So it's earlier in the short lex word order. But men is shorter than woman, and so men is earlier than woman in the short lex word order, and woman is the same length as women, but it precedes it in the dictionary, and so this is the ordering of man, men, woman, and women. I gave this talk in France, and I thought it was quite interesting that whereas man is weaker than both woman and women, femme in France is not. It's in German, I thought about it. In German, the women are weaker as well, which actually contradicts what I've experienced in Germany, but there you are. Anyway, so short lex geodesic is a word which precedes all other words representing the same group element within the short lex word ordering, okay? And so I'm interested in languages for a group. So a language for a group is, you know, that's the wrong arrow, and I'm sorry about that. That's supposed to be, a language for a group is a set of words that maps onto the group. So that's the wrong arrow. It should have two heads and not two bars. I haven't noticed that. So the short lex geodesics are a language which is also a normal form. That is to say, it's a language that maps onto the group one-to-one. Okay? So that's what I mean by a language. That's what I mean by normal form. So that's just general stuff. Okay, so words can be viewed as paths, or they label paths in the calligraph for G. So this is some calligraphs. It's supposed to be a colloquium, so I guess I put this general stuff in. So a calligraph is a graph whose vertices correspond to the elements of the group. There's one vertex which is the identity vertex, and there are the edges correspond to the generators there, directed edges. Everybody knows this, I think. Directed edges labelled by the generators. There's a directed edge labelled by X from the vertex which corresponds to the element G to the vertex which corresponds to the element G times X. Okay? So there's the calligraph for the free group on two generators A and B. There's the calligraph for the free abelian group on two generators A and B. So there's an edge, a path labelled A times B from the identity to this vertex up here. There's also a path labelled B times A from this vertex to that vertex there. And because in the free abelian group A times B equals B times A, the two paths lead to the same vertex. So that's, so I've left off some of the edges because there's not space for them all, but in this graph all the horizontal edges are A edges and they all go to the right, and all the vertical edges are B edges and they all go upwards. There's an edge labelled B inverse that goes in the opposite direction to the one labelled B, and so on. Okay, and there's the calligraph for a nice affine Coxeter group. I've put a little star where the identity vertex should be, and in this group you have the relations A squared equals the identity, so I haven't put labels on the edges because where there's an edge labelled A, there's one going the opposite direction, also labelled A. Okay, so there's no arrows on the edges, and you see lots of hexagons because of these relations here, which are relations at length 6. Or the left-hand side is length 6. Okay, so those are some calligraphs, and everybody I think in this audience knows what a calligraph is, almost certainly, but then you may not all know what an automatic group is. So a group is automatic if it has a language, that is to say it has a set of words which maps onto the group, that is regular, that is to say it's recognised by a finite state automaton, and that's on the next slide. Okay? So a language that is regular and it satisfies this property here, which is called the fellow traveller property. So the property says if there are two words, there is a constant K global for the group, such that, I'm sorry, the punctuation of this is slightly wrong. There exists a K such that if V and W, such that if V and W are elements of the group that satisfy either V is equal to W in the group or V is equal to W times X in the group for some generator X. If that is true, then for V and W, the words V and W, K-fellow travel in the group. I'm sorry, that's very badly structured, that sentence. So this is a picture of it. Here are V and W, which V is the bottom word and W is the top word, and there's, I think, V is equal to W times X, so there's a single generator apart at the end, okay? When you have two words like that, or if they actually met at the same place in the end, then as you trace them out in the Cayley graph, they stay a bounded distance K, at most K, apart, okay? So that's the fellow traveller condition. So a group is automatic if for all V and W in the group which satisfy one of those two equations at the end, then V and W, K fellow travel in the Cayley path, or the paths that they labelled it, okay? So G would be bi-automatic if you have this fellow travelling when between V and X times W, whenever V was equal to X times W. Okay? So when multiplication on the left by a generator gave an equation, then we would also have fellow travelling. So automatic means whenever you have multiplication on the right by a generator giving that equation, then you have fellow travelling. Bi-automatic means it also happens when for multiplication on the left. So the group is short lex automatic if the set of short lex minimal geodesics gives a language which satisfies this condition, which is regular and satisfies this fellow travelling condition. This isn't tremendously important to this talk, not to the understanding of the talk, it's just so you don't need to have very deep understanding of this to understand this talk. Okay, so if a group is automatic, then you can solve the word problem. You can rewrite any word over the generators of the group to a representative in this language in quadratic time, and hence you can solve the word problem in quadratic time, at worst quadratic time. Okay? If you have bi-automaticity, then you can solve the conjugacy in the group, but the solution for the conjugacy problem is, that is implied by bi-automaticity is slow. Okay? But automaticity implies a fast solution to the word problem. Bi-automaticity implies also a slow solution to the conjugacy problem. Okay? So, this picture shows the short lex geodesics in the free linear group on two generators. Those are all the words, this is assuming that A is less than B in the dictionary ordering. These are all the words of the form A to the I, B to the J, shown as blue lines, blue parts in my Cayley graph for Z squared. And that's the automaton that recognises that set. So how do we read that? Okay. So this little arrow pointing at this vertex means that this vertex is the start place in this automaton. The automaton is a finite graph, as you can see. And there are edges in it which are labelled. And the idea is that a word is accepted by this automaton, a string over A, B, A inverse, B inverse is accepted by this automaton if when I start at the start vertex and follow it through along edges in the directions of the arrows, right? That are appropriately labelled, then any path that I can trace out and wind up at a nicely labelled vertex, a nicely labelled vertex being one that has a little ring around it, as all the vertices in this graph do, in fact, but they might not. Okay? Any word that I can read out in that way is accepted by that automaton. So, AB is accepted by that automaton. AB inverse is. A inverse, B inverse is, because they take us from here to nice vertices. But ABA is not. Okay? So this machine, this automaton, recognises all words of the form A to the I, B to the J, where I and J are integers. Okay? And nothing else. Right? So that's automaticity for you. Okay? Now I also want to talk about rapid decay. So, a group satisfies rapid decay if the operator norm for the group is bounded by a constant multiple of the Sobolev norm, of the Sobolev norm, for some R and some L. Okay, I forgot to say for some R. So what on earth are they? Well, the operator norm is this, and the Sobolev norm is that, right? Okay, so that's the operator norm, and it's defined in terms of that and that. Okay, so it's a nasty, messy quotient of two infinite sums. Okay? So that nasty, messy thing has got to be bounded by a constant times that nasty, messy thing. And if that's true, then the rapid decay property holds. You get to choose L, and also you get to choose R, which I forgot to say. Okay? You get to choose L so long as it's a length function. Okay? So that's the rapid decay property. So why on earth are we interested in rapid decay? Because it's very useful. If the rapid decay property holds for a group, lots of other things are true. So the Novikov conjecture and the Bancon conjecture are related to rapid decay. You can often deduce the Bancon conjecture if rapid decay holds, and we'll talk about that in a little bit. Okay, so this property, rapid decay, was proved by, well, it was defined for free groups by Hagerup. Well, he identified it as a property, and then Jolly-san proved it for word hyperbolic groups, and so it's known to be inherited by subgroups and by free and direct products of groups with this property, etc., etc. It's known to hold for groups that act appropriately on cat-zero cube complexes, for Coxeter groups, right-angled Artin groups, so actually for some Artin groups it was known already. Also for mapping class groups, which means it holds for the break groups because they're mapping class groups, so for other Artin groups it was already known. And it was proved, actually, just around the time that we proved our stuff, but slightly earlier, it was proved to hold for groups that were hyperbolic relative to subgroups that had it by Druter and Sapir. Okay, so it was known, it's known to hold for quite a lot of groups. Okay, and the Bancon conjecture is even more mysterious to me. It relates the K-theory of the reduced C-star algebra of a group to the KG homology of the classifying space of kappa G actions, whatever that means. So it proves that some maps between the two things are isomorphisms. And this too is linked to all kinds of other conjectures. The only one that makes any sense to me, I think, is the Kaczynski-Kaplansky conjecture, which proves that, which is known to hold when used as sweeping torsion-free, given Bancon, right? And this proves that the group ring, the rational group ring, contains no non-trivial idempotents, okay? So Bancon is known to hold for a range of groups, so I'm not aware that it's particularly interesting whether or not it holds for Artin groups. It would be much more interesting if it didn't, but it does, because it proved, at least for our Artin groups, it's proved. But it was previously known to hold for Coxeter groups, it was previously known to hold for right-angled Artin groups and for Bray groups, but to my knowledge it wasn't actually known to hold for many other Artin groups, although in fact you can derive it for a few other spherical Artin groups using essentially Schick's work. Maybe for all other spherical ones, I forget. But it wasn't previously known to hold for a large number of Artin groups, for the large number that we derived it for. Okay, so I think the reason that the fact that we proved rapid decay was interesting, really, was because of this result of Lefort, which says that if a group satisfies rapid decay and has an appropriate action on a cat-zero metric space, then actually it satisfies Bancon. So this is a very useful result of Lefort, which meant that subsequently Bancon was derived for a huge number of groups using, using this result. And it's Lefort's result that we use to prove that Bancon holds for our Artin groups. Okay. So that's enough of the background, the general background. Let's get over to Artin groups. Okay. So an Artin group is a group with a presentation like this. It's got a finite number of generators, and then the relations, all the relations are of this form. They're braid relations. So they're relations between two words of the same length, each of which is an alternating product of two generators. So the first one starts with the generator xi, the second word starts with the generator xj, and it's a product of xi, xj, alternately. And the two sides of the equation have the same length, mij. Okay? So, and we have such relations for all I, or potentially such relations for any pair of generators x, I, xj, where I is not equal to j. One such relation for each pair. At most one such relation for each pair. If there's no such relation, well, I'd say that mij is infinity. Okay? So such groups are related to Coxeter groups because there's a Coxeter group with a presentation just like that, except that each of the generators xi is defined to be an involution. Okay? And therefore every Artin group has a Coxeter group as a quotient. So every such group is associated with a matrix, a symmetric matrix. It's made a symmetric integer matrix because mij is equal to mji. And then a Coxeter graph, whose vertex, which is a finite graph with n vertices and with an edge labelled by mij joining the vertex I to the vertex j. Okay? So such a graph is called a Coxeter graph, and there's an Artin group, which I'm going to call G of gamma associated with such a graph, and there's a Coxeter group, which I'm going to call W of gamma, W for file, also associated with such a graph. So W will always be the Coxeter group, G will always be the Artin group, and they'll both show up from time to time. Okay. So Coxeter groups are linear, they're generated by reflections in hyperplanes, HI in n-dimensional real space, and then the product of two reflections is always a rotation through the angle 2 pi over mij. And there's this thing, this two n-dimensional manifold, y sub w, on which the Coxeter group acts freely and properly discontinuously, which is defined in this way. There's this, which I don't have to go into, which will come up again. All right, so there's this two n-dimensional manifold y sub w that the Coxeter groups acts on. Coxeter groups have polynomial time solutions to the word problem, which they derive from their representations as linear groups. They're also short-lex automatic, which was proved by Brink and Howlett, and so I suppose there's an Australian connection with that result. And so they have quadratic time word problem because automatic groups always do. They have regular geodesics, that was also proved by Brink and Howlett. And they have soluble conjugacy problem, that was proved by Cramer. The solution to the word problem that I actually like is much slower than the one that these groups get from their linear representations or from their short-lex automaticity, because it's just really pretty. And I'm going to mention it because we do something a bit similar, okay? So Titz's solution to the word problem basically rewrites using the braid relations and nothing else, that and cancellation. So you take a word and you want, all right, so you can reduce any word to a geodesic word in this way, okay? So you take a word and you look to see if there's any occurrence of either side of a braid relation within that word, and if there is, the only way that this word can be shortened is by cancellation of, is by deletion of a square of a generator, which is a subword, or by replacing one side of the braid relation by the other side of the braid relation, and then subsequently doing cancellation. So you look through, so if you look at a word, the only way it can be cancelled is if it's either got a square of a generator in there, or if it has some occurrence of one side of the braid relation in there. And if it does, then some sequence of application of braid relations will lead to a square of a generator and appearing as a subword. Okay? So you look at this word, and you see there's an ABA in there. So you try changing it into a BAB. There were no other, in this group, the braid relations were all up there. Oh no, there's an ABA there as well. But so some sequence of applications of braid relations will have to lead to a reduction if this word is going to reduce. So we try one. We try replacing ABA by BAB. And then we see BD, which is up there in the BD equals DB. So we try replacing that BD by a DB. And then we see there's a BE, and that's up there in the presentation as well. So we replace that by an EB. And then we get a BCBC, which is also up there in the relations. So we replace that by CBCB. And then we see there's a BAB in it, so we try replacing that by an ABA, and look, we got an A squared. So we can delete it. So we found a sequence of applications of braid relations, which gave us a reduction. Okay? That's Titz's algorithm. Now that's an exponential algorithm. So it's not very good, but it's what we want today. Okay? So we're going to do something like this. So we're not going to have braid relations, but we're going to have some set of relations which preserve length, and some sequence of these length-preserving relations. We apply that, some sequence of that, in order to force a reduction. Okay? It's just they're not going to be quite as nice as the braid relations. Okay? So that's what's going to happen. So we're doing Artin groups now. We're not doing Coxeter groups, we're doing Artin groups. So they were introduced by Emil Artin, actually as early as 1926. Somehow he wrote his paper in 1926, and then he wrote a very similar paper in 1947 with the same title, except the first one was in German, the second one was in English. But anyway, and that's why they're called Artin groups. So his paper was about braid groups. So there's a braid group presentation there. So Artin represented the braid group G of AN as the group of braids on n+1 strings. So this is the braid, and he found a presentation for the group, and he solved the word problem by this representation as a set of braids, of actual braids. All right, so this is the generator X1 of the braid group G of A3, and this is an element delta which is the product x1, x2, x3, x1, x2, x1. You can see that because there's x1, then this here is an x2, and this is an x1, and then I guess this is one, whatever. Maybe I've got it upside down, it's possible. Anyway, that is that product of the generators. So this is x1, x2 would be the one that swaps these two, and x3 would be the one that swaps those. And the half twist can be written as x2, x1, x3, all squared. Okay, now remember that because you'll need it again. So, all right, so Artin introduced these groups, and then Higman's student, Garside, he studied it further. And he introduced a beautiful normal form for the braid group. He found the quotient of braid monoid, which is the monoid of the same presentation, but it's monoid, okay? So he represented every braid as a product of the form delta to the k w, where delta is, we just met delta, right? Where w is a positive word in the generator, so it's in the monoid. So everything in the monoid is represented as a quotient of w by delta to the minus k, if k is negative, and otherwise it's a positive word. Okay? So it's either a positive word or it's a quotient of a positive word by the power of delta. Okay? And with this presentation, Garside could solve the word and the conjugacy problem, although Folk has a much faster solution to the conjugacy problem. But it's based, I think, on the... All right. So Garside realised that there were other groups he could handle in the same way, and so he started to do that. And then Rees, Saito, and Deline worked on this and got a lot further for the Artin groups of spherical type, that is, the Artin groups for which the associated cost group is finite, and then Thurston came along and Charney came along and did more. They proved bioticity for these groups. And then de Hornoy and Paris, they built on this and they defined Garside groups, which are groups with more general arithmetic properties that you see already in the spherical type Artin groups, which are found as quotients of Garside monoids. And so people have found polynomial time solutions to the conjugacy problem for braid groups and all Garside groups, and again, Folk's done a lot of this. So then Charney and Altobello moved from the groups of spherical type to those of FC type, which, well, I shan't define those, but, well, they're defined on the slide, but just going further, they could take essentially the results that were known for the spherical type Artin groups, they could take further to a larger class of groups. And this was all based on normal forms. Okay, this is all a normal form approach to the study of these groups, I would say. And de Hornoy and Gödel, they proved a property called property H, which is close to hyperbolicity of these groups. These are very much not hyperbolic groups, or very much, well, they aren't hyperbolic, because most of them have z squared inside them, so they can't be hyperbolic. Okay? But I would say this is a normal form approach to Artin groups, which goes from braid groups to spherical type groups and further. Okay? So that's spherical type. But then there are lots of other Artin groups as well, which are not spherical, and for which these techniques that Garside essentially started on don't work. Okay? So they've been studied, to date, they've been studied quite, or until recently they were studied quite differently. They had a sort of, although Artin groups are not hyperbolic, can almost never be hyperbolic, they have a sort of hyperbolicity about them. And that was identified by Appel and Shook in 1983 and 1984 to prove, in a sort of geometrical way, various things about these groups. They could solve the word problem, they could solve the generalized word problem, and the conjugacy problem. They could prove that the groups generated by subsets of the standard generating set, the one that we give in the presentation in terms of, that they were Artin groups too, with the appropriate subdiagrams of the original diagram for the original Artin group. And in that way, they invented as subgroups in the bigger Artin groups. All these groups are torsion-free, and they can prove that in these large type Artin groups, I forgot to say what those are, but those are the ones for which all the integers are at least 3. So there's no commuting relations amongst the standard relations, right? For as long as none of the standard relations imply commuting, then they could deduce all these things, and in particular they could deduce that the subgroup generated by the squares of the generators are free groups. And afterwards, too, it's conjectured that this held in all Artin groups. Okay? But this was, the original result was proved in Appel and Shook's paper. Now people built on their work. Pfeiffer proved that the extra large groups of this type, so those where all the integers involved are at least 4, were biautomatic, using a curious normal form. I mean, not a very natural normal form, right? But he could prove biautomaticity. And Brady and McCalmont proved biautomaticity for some of the large groups, essentially these 3-generator large groups, but actually it goes further than that, but not all of the large groups. And then Steve Pride studied triangle-free groups. Those are the ones where there are no triangles in the Coxeter graph with 3 finite numbers in labeling the edges. Okay? And Danny Chermak studied something called locally non-spherical groups. So they both extended the class, the results of Artin and Shook beyond large and extra large, to further classes of groups, right? And I just mentioned as well, I wanted to mention as well that Hemiller and Meyer, they studied right-angled Artin groups, which are in a way quite different, but they're certainly not spherical. So these are the ones where all the relations are either, all the relations apart from free relations are simply commuting relations. So the Coxeter graph, all the edges are linked by the 2, where the 2 generators commute, or infinity, where there's no relation between them. Okay? So that was what was previously known about the groups that are very much non-spherical. The other side, Artin groups split into the spherical ones and the kind of largish ones, and then of course there are various mixtures of the 2. So this is the other extreme to spherical. That was what was previously known, but what I wanted to say, and I didn't know how to say it in the slide, partly because it's full up, was that this is a sort of geometrical approach, whereas I would say that what's known about the spherical and the spherically related groups is all normal form related, okay? So there were some general results about Artin groups which are known, and there are also some conjectures of things about Artin groups that are unknown. So there's a complex, there are various complexes associated with Artin groups. You can take the, we had that Y sub W before, it was a 2n-dimensional manifold that you get for a Coxeter group. And you can factor out the action of the Coxeter group there, and you get another complex whose fundamental group is the Artin group. I think I have that right. I meant to check this out. It might be a pure Artin group. I think it's a pure Artin group, which means the, right, so I'm sorry about that, the subgroup where the kernel of the map onto the Coxeter group. Anyway, it's related, so I'm sorry about that. So the K-pi1 conjecture for Artin groups states that the universal cover of that complex XW is contractible, so that we have an Eilenberg-MacLean space for the group. So I guess the universal, yeah, so there's something not quite right in there, I'm sorry about that. So the K-pi1 conjecture is proof for Artin groups of spherical type, but it's open. And it's equivalent to conjectures about 2 further complexes, the Deligne complex and the Salvetti complex for the group, okay, which are homotopically equivalent to the universal cover of XW. So I'm not going to be talking much about those. So it's known that Artin groups are always infinite. It's known that the subgroup of an Artin group generated by a subset of the standard generators is always an Artin group of the corresponding to the appropriate subdiagram. Okay, that's why I know that Artin groups can't be hyperbolic, because Artin groups with two generators cannot be hyperbolic because they're essentially braid groups and they contain z-squared subgroups. Well, no, they're dihedral Artin groups. They look a lot like, yeah, they're essentially braid groups. Most of them are. Not braid groups, spherical type Artin groups. So the parabolic subgroups of Artin groups, in fact, are recently proved to be convex. That's using the Salvetti complex. It's a result that's on the archive at the moment. And the Artin monoid, the monoid with the same presentation, always embeds in the group. That was proved by Paris in 2001. And that Titz conjecture was solved in 2000. So those are all general results about Artin groups in general that are known to be true. But there are lots of things that are not known. It's not known in general if an Artin group has a good normal form. It's not known in general if it has soluble word problem or soluble conjugacy problem. It's not known in general if the group is automatic. It's not known what the centre of the group is. It's not even known if it's torsion-free. But if the K-pi1 conjecture holds, then it is. It's not known in general if Artin groups have rapid decay or if they satisfy Van-Gon. Okay, it's known for spherical type ones, and some of this now we know for sufficiently large groups. Okay. So I need to tell you what a sufficiently large group is. So I say that a group is sufficiently large if, whenever I see a commuting relation between two generators, it has to correspond to a subdiagram. Any subdiagram of the group it fits into that contains that edge has to be either that type or that type. You can't see a 2 in the diagram unless it either appears in a triangle of 2s or in a triangle that contains at least one infinity. Any triangle containing 2 is like that or like that within the diagram that defines the Artin group. Okay, that's what I mean by sufficiently large. Commuting is controlled. Okay, large would mean that you didn't ever see any 2s. Extra large would mean that you didn't even see 3s. But sufficiently large means when you do see 2s, you only see them in triangles like that or triangles like that. But no other triangle can contain 2. Okay? So large and extra large are contained in my definition. Triangle free is contained in my definition because you wouldn't see any triangles. But our definition doesn't quite match Schermach's definition of locally non-spherical. There are groups that are locally non-spherical that are not sufficiently large. There are groups that are not sufficiently large. There are groups that are sufficiently large that aren't locally non-spherical. Okay? Right-angled Artin groups are sufficiently large. Okay, so what we can do with these groups, any group that's sufficiently large, that is sufficiently large, we can define, we can recognise the geodesics, and we can rewrite any word to geodesic form. We can rewrite any word to short-lex geodesic form. Okay? And we can do so very quickly. If we have a word that is short-lex geodesic, and we stick a generator on the end of it, with a single move, a single sequence of moves, sweeping through the word, we can reduce it to a geodesic. Remember, it's Baxwell prefixes geodesics, it's short-lex geodesic. With a single sweep of moves, we can reduce it to a geodesic or to a short-lex geodesic. And I'll show you how. Okay? And each of these sweeps of moves is a composite of basic moves, and a basic move is either a braid, a move is a single application of a move to a subword on 2 generators, or it's a single application of a subword to a set of generators which are pairwise commuting or free. Okay? So a simple move is either one of those 2 types. It's either a move on a braid pair of generators, on a 2-generator subword, or it's a move on a commuting pair of generators. A commuting or free set of generators. So it's either a beta move or it's a kappa move. Okay? And we can reduce any word of the type I described. We can reduce any word to a short-lex geodesic and at worst quadratic time. Well, that's true for any automatic group, right? We think we can do it in linear time. Okay? So the beta moves are the moves that we would use to reduce any word within a dihedral Artin group. And the kappa moves, as I said, are basically the moves we would use in a right-angled Artin group. Okay? We do need the sufficiently large condition. This doesn't work in braid groups. Okay? The moves we use, there are words in the braid group, GA3, where if we applied our techniques to them, they would not reduce to short-lex geodesic form. Okay? So it all works because it works in the dihedral Artin groups. Okay? Or the braid moves work in dihedral Artin groups. So I'm going to talk a little bit about those. So a dihedral Artin group is a 2-generator Artin group. So it's a group on 2 generators with a single braid relation. Right. So suppose I'm in such a group. And suppose the M is the defining parameter for such a group. Okay. So suppose I got a word over the 2 generators of a dihedral Artin group. Then there are 2 numbers I'm interested in. There's P, which is the positive number associated with that word, and there's like a positive parameters, they're both of them positive integers actually, but there's the positive parameter and there's the negative parameter. So P is for positive, N is for negative. So positive parameter is the minimum of M, the defining integer, and the maximum length of a positive alternating subword within W. The N parameter is the minimum of M and the maximum length of a negative alternating subword in W. So they're both positive integers. Right? But P measures something positive about the word, N measures something negative about the word. So here's a word, and it's A, B, A, B, A inverse, B inverse. So it's got a positive alternating subword here, and it's got a negative alternating subword there. Okay, that is a opposite, yeah. So this one has length 4, this one has length 2, and we're in DA3, which is defined by the integer 3, which is less than 4, but bigger than 2. So the positive parameter here is 3, because 3 is less than 4. The negative parameter is 2, because 2 is not less than 4. Sorry, 2 is less than 4. What am I talking about? Yeah, because 2 is less than 3. Yeah, 3 was the M. So it's 3 for that, and it's 2 for that. So P of W is 3, and of W is 2. Okay? So then, there are these two French guys, Meres and Mateus, who I've never met, but maybe you have.
Mm.
Yeah? And they discovered that in a dihedral Artin group, a word is geodesic if the positive number and then the positive parameter and the negative parameter of the word are at most M. And in fact, it's the unique, W is the unique geodesic representative of the element it represents if the sum of those two things is less than M. Otherwise, there are more than one geodesic representative of that word. Okay? So we look at the word we just looked at, and there P is 3, and N is 2, and 3 plus 2 is 5, which is bigger than, 3, which was M. Okay? So we do the sums, and we discover that word must be non-geodesic. But it has lots of geodesic subwords, because that's a geodesic, because that's length 3. And so because P is 3, and N is 0, and 3 plus 0 is 3. And this one is also, and this P is 2, and N is 1, and 2 plus 1 is 3, and here P is 1, and N is 2, and 1 plus 2 equals 3. So those words are all geodesic. Okay? And those are the words we like. These ones here, they're special. They're critical. They're critical subwords. And I need to define what a critical subword is. Okay? Right, so to define critical subwords in a dihedral Artin group, I need to talk about the Garside element. So we met that before. Well, we sort of did. We met a word called delta before. And this delta is just like that last delta. It's special to the group. It's central in the group, or maybe it's square is, it depends, on the value of M. So it's the product, it's the left-hand or equivalently the right-hand side of the braid relation. Okay? Either of those words represents the Garside element. Okay? So conjugation by that element induces a permutation in the generating set. Either A conjugates to B or A conjugates to A. Okay? Right, so it might be a triple permutation of the generating set, or it might swap them, but it is a permutation in the rate. Okay, so now a geodesic word is critical if it has the form that it's a positive alternating product of the two generators, followed by something, followed by a negative alternating product of the generators, and it's a word that is also geodesic, so that this psi here must not interfere, but it mustn't essentially add on to the end of this positive alternating word and give a longer one. So the word splits into a positive alternating word, something psi, and the negative alternating word, and the maximum length of the positive alternating subword is P, and the maximum length of the negative alternating subword is N. Okay? The psi is in the middle. Either it's of that form, where it begins with a positive thing and ends with a negative thing, or it starts with a negative thing and ends with a positive thing and there's something in the middle. Okay? And the reason I called that one delta psi is because this one has a friend, which is that one. Okay, so these critical words come in pairs. Right? You get from one in pair to the other by just like this. So if this starts with, I don't think I explained my notation, but this is a positive alternating subword that starts with X and has length P. And this is a negative alternating subword that ends with T to the minus 1 and has length N. So the fact that the suffix N is at the end means that this marks the end of the word. The fact that this is a prefix, P, means that this alternating subword starts with an X. Right? So that word has that word as its friend. This word starts with Y inverse, this word starts with X. Right? This word ends in T inverse, and this one ends with Z. So T is different from Z, X is different from Y, but I'm not saying anything about the relationship between X and T, or Y and P. Okay? All I'm saying is that X and Y are different, and T and Z are different. Okay? So those two are friends. And we can also have critical words that have length, that start with a positive alternating subword of length M. But I'm not talking about those simply because it would just mess up my slide. Right? But we do allow critical words that start with a positive alternating word of maximum length, or end with a negative alternating subword of maximum length. We allow those critical words of that type as well. Okay, but they come in pairs, and I'm clearly running out of time. So they come in pairs, and that shows two in a pair. And a beta move takes one in a pair to the other in a pair. Okay. So that word I was looking at before, it has all these critical subwords in it, and I can apply a beta move to one of those critical subwords, and I get another word. Okay. And so I just did that. ABA inverse had a friend B inverse AB, and when I applied that move, I got a free cancellation. I got a word which freely cancelled. And, in fact, you can prove, in the dihedral Artin group, if a word reduces, if a word is not freely reducible, if it's not short lex minimum, then one of these moves will reduce it. Okay? That happens in the dihedral Artin groups. Okay? So, in fact, if you take any large type Artin group, then those kinds of moves, if a word is not short lex minimal, there must be a sequence of moves for those types that reduces it. Okay? And originally that's what Derek and I proved. Okay? But then we realised we could do more than this. We could do these kinds of reductions when we had commuting moves as well. Okay? So we also have these kappa moves, which basically, within a subword of which work in right-angled Artin groups, which just move things that commute past each other, okay? So we have two kinds of basic moves. We have beta moves, which I've just shown you within a dihedral Artin group, and we have kappa moves that just do the commuting stuff. And in sufficiently large Artin groups, sequences of moves like this, of this type, reduce everything. Okay, so here is an example. Here's a group, and it's sufficiently large. And look at the word A inverse BA, DE, C inverse BC, ABA. Okay, and skip to the next slide. So I've written my word along the top of this wavy stuff, okay? A inverse BA, DE, C inverse BC, ABA, right along the top, okay? And so A inverse BA in this group, the presentation was back there. ABA equals BAB, ACA equals CAC, then B and C are related by a word length 4, and B commutes with D and B, okay? So A inverse BA is a critical word because it has length 3, it's got a negative bit of length 1 and a positive bit of length 2, so it's friendly with BAB inverse, and I can replace it by it. When I do that, then my word, instead of going along the top of the word, the first wave goes on the bottom, okay? And when you do that, you get a subword, B inverse DE. Now B commutes with D and E, so we can bring B inverse past DE, and we get DE B inverse. So now my word is written on the bottom of the first two sections and on the top of the remaining ones. So then I get DE B inverse C inverse BC. So on that third blob, I have B inverse C inverse BC. And there was M was 4 between B and C. So I can replace B inverse C inverse BC by CBC inverse B inverse. And then I'm going along the bottom of the first 3 bits and on the top of the last bit. Then I get B inverse AB, which is critical. I can replace it by AB A inverse, and the A inverse then cancels with the A, and I've reduced, or I can reduce freely. So that wave of reductions gave me free reduction. And here's the word, another word, written on the top of this. And now if I can work from right to left, do the same trick, I get this word here, which has the same length as the original word and doesn't show any free reduction, but assuming that A is less than B is, and so on, A is less than A inverse is less than B is less than B inverse is less than C is less than C inverse, this word is lexicographically less than that word, and so it's earlier in short lex. And so our theorem says, if I've got a sufficiently large group, if W is geodesic but WA is not, then a rightward sequence, the first type, will reduce to a geodesic. If W is short lex geodesic but WA is not, then a left reducing sequence will reduce in short lex. okay, but not a length. And it also says that if you've got distinct geodesics representing the same element, then basically they're written, well, it says a lot of things, but basically they're written over the same generating set. Okay, there's no generator that appears in one way that doesn't appear in the other. Okay, so I know I'm really running out of time. I've only got 3 minutes left. So using that, everything I wrote down there, you can prove that these groups are short lex automatic, and the set of geodesics, well, the set of geodesics is regular as well. And I could write down an automaton that recognises the geodesics for you. I could write down an automaton that recognises the short lex geodesic and prove the fellow travelling property and everything using that information that was on the last slide. That was the essential information to prove that. Okay? And you can deduce very easily that the parabolic subgroups of these groups are convex because I just told you they're written over the same generators. Two geodesics representing the same element are written over the same generators. So it follows immediately from our results that parabolic subgroups are convex. And this has just been proved for Artin groups in general, right? But it is, we can show it to be true for the sufficiently large groups using our results. Or we could. We did, I guess. But now we understand the geodesics and we understand the short lex geodesics, so we can do a lot. Because we have a nice normal form. So we can prove rapid decay. Okay? So it's complicated proving rapid decay. So I'm not really going to go too much into it. Basically, to prove rapid decay, you have to prove this connection between these two norms. So you prove it by essentially proving the same result, but for words of restricted length. So you prove that when you take the words of length k and the words of length l, and you combine them together, you have to control the way that words of length k and words of length l are multiplied to give words of length m for each pair of integers k, l, and m. So that's what you have to do. So if you can understand the way that words of length m factorise as words of length k and words of length m, you can control that, then you can do everything. So that's what you need to be able to do. If you had polynomial bounds on the number of factorizations of the word of length m as product of elements of length k and l, then you'll be laughing. And you can do that for free groups, and you can do it for hyperbolic groups. Unfortunately, you can't do it for Artin groups, so large type we tried for a bit. But you can do something relating to it. You can prove, well, you can't do what I wanted to do because this element delta is such a nuisance. The powers of the element delta have loads and loads of factorizations, and you can't control them polynomially. But we managed to do it nonetheless by, well, no, I'm not going to go into details, but we managed, if we just looked at factorizations of certain types where this element delta didn't get in the way, then we had the polynomial bounds that we wanted. So what you have to do, basically, is you have to look at a factorization G of an element of length K and an element of length L, and then you have to transform it into a different factorization of G into a product of 3 elements, where you don't allow the bad factorizations that involve delta to get in the way. Okay, so I'm not going to go into any details, but that's what you have to do. You have to somehow deal with the bad elements delta, and then with these nasty polynomial bounds, you need it. Okay, whole set of polynomial bounds, you need it, and we proved that they held because we knew a lot about the ways things factorized. Okay, and so we managed to prove the rapid decay condition, and then we managed to deduce bound con because there was some very useful work of McCammond and Weiss, which gave exactly the action that we needed. Okay? So we used that to deduce bound con for these groups. And that's what's going on here. And then Derek and I had a look at the conjugacy problem, and we can solve that in cubic time. Now, we didn't have to produce an algorithm because it was there, given by Artin and Schrupp. But we can prove that it works in cubic time because we know all about geodesics, basically. In fact, we needed a nice geodesic normal form that worked under left multiplication as well as right multiplication. And ours doesn't. The short lex minimal geodesics don't work as well under left multiplication, but Python proved these groups by automatic. So we know there is such a normal form. So actually we used Python's normal form to do the dirty work here. But because we understand geodesics, we can prove that everything can be done fast. Okay, so that's the algorithm for those, which we don't have time to go into. And another thing that I did was I talked to Eddie Goodell, and he could deduce a property H for spherical type-Artin groups, which basically means that all rewriting can be done using certain length-preserving moves of a particular type. You can prove this for spherical type-Artin groups. We can prove it for our groups as well. And so there's a large class of groups for which property H holds, which are various products of amalgamated free products of groups of R type from his type. Okay. So we don't know if our algorithm, if our reduction works in linear time. We suspect it does, but we haven't proved it. Okay. We don't know if Goodell and Hornweiler's condition H holds for all Artin groups. We know it holds for a hell of a lot of them. We don't know if all sufficiently large groups have a nice biautomatic structure. Well, we know it has one because Python produced one, but we don't like it. We like ours better. It's just not biautomatic. We realise that our proof of rapid decay looks an awful lot like Brueggemann's and Pierce for relatively hyperbolic groups. But our result doesn't imply theirs, and their result doesn't imply ours. So our techniques aren't quite like ours, they just look a bit the same. But recently, Mark Sapir produced a more, he found another proof of rapid decay which uses centroids. And he can prove that the centroid property holds for the groups the relatively hyperbolic groups that they were studying. So his proof is a generalization of their proof, and it's also a generalization of ours. So he can hold, that is, he can prove that the centroid property holds for our groups, just as it holds for theirs. So there's a lot of the same stuff going on there. So, I mean, the fact that the centroid property holds follows very easily from that messy slide I didn't let you look at just now. Okay, there are a pair of messy slides, one with a nasty picture on it and one with lots of polynomial conditions. So once you have those, you can prove his centroid property very easily. Okay. So, oh yeah, I looked for something strange at the end. Right, so what happens when I go on? Right. So I finished now. Okay. Yeah, I can hear it. There you are.
Okay. Any questions? Newcastle.
I can't too quickly for you all.
I didn't understand the age condition. Just quickly.
Oh, this age, yes.
Yeah.
So it's you have the braid relations which are between positive words, right? So the positive word W, it can factorize as U times V, and the negative word W prime, it factorizes U prime times V prime. But there are conditions on U and V and U prime and V prime. I think you can't have, see, U and U prime can't, the prefixes can't be trivial. So if you don't like the prefixes to be trivial, then you can flip the U onto the, you can invert the U and you can invert the V prime, right? And so you can bring them over to the other side. You don't allow the prefixes to be trivial, you can turn the relation to that one. If you don't allow the suffixes to be trivial, then you can multiply on the right, okay? You can multiply on the left by U inverse, and on the right by V inverse, if you don't allow the prefixes to be trivial. Or, and then that goes on the left-hand side of the reduction, right? Do you see what I mean? Or you can multiply on the right by V inverse, by V prime inverse, and on the left by U inverse if you don't allow the suffixes to be trivial. But the bit you don't allow to be trivial has to go on the left. So you're not allowed to turn it into a word where the bit that's been inverted is non-trivial on the left-hand side of the reduction. You see what I mean? So you take your positive relation, you're not allowed to turn it around in all possible ways. You're not allowed to rewriting with it in all possible ways, because obviously to move from the positive relation to the rewrite rule, you have to invert by something. And the thing that you're allowed to invert has got to be non-trivial when it's on the left-hand side of a reduction. Isn't that right? So there's a limitation to what rewrites you're allowed to do with your positive relation. You're allowed to do more than just a positive rewrite, but when you've got negativity in your rewrite, then you're restricted from what you're allowed to do.
So is this a weak form of hyperbolism? Because
Yeah, it's
maybe it's the then algorithm?
it's a weak form of hyperbolicity, but so why is it a weak form of hyperbolicity? Why do they consider it?
Because it's like the Dane algorithm.
Exactly, yeah. I don't see the geometry.
Yeah, it's like a Dane algorithm. I guess it's like a Dane algorithm.
But because you talk about break relations, this will not work for groups that don't have.
Sorry?
So you look, I mean, everything starts with a break relation.
Everything starts with a braid relation, but
So this won't work for really arbitrary groups.
this
With
condition.
arbitrary present.
Well, I think it's maybe something that you could generally discuss for something where the relations were all positive, isn't it?
Okay.
But it's how much negativity you're allowed to apply to these positive relations, isn't it? That's controlled. So I mean, this isn't my condition. This is de Horn Goodell's
Right.
condition. So so my input to this is just showing that this works for our groups, which it does. It's quite easy to see that it holds for our groups. It wasn't very hard work, but it does hold for them. So when this property, well, this is, I think this is 8 that I've actually put down. 8 sharp is a slight variation of this, and I think when 8 sharp holds, then you can prove. When it holds for a class of groups, I think that it holds for amalgamated products of them. So 8 sharp is somehow more useful than H. And I think de Horn and Goodell proved 8 sharp for the spherical type groups, and therefore they have it for all the, what are they called, F something, FA groups. These are the groups that were considered by Charlie and our student, he appears on the previous slide.
FC?
FC, yes, FC. Right, so I can remember what Johnny's co-author is. Altobelli. Johnny and Altobelli considered FC groups, and FC groups are these amalgamated products of, amalgamated free products of spherical type groups. FC stands for flag something, doesn't it? Flag complex, I think. I think they're groups for which the, what are these complexes? The Delsart complex, is it? The Salivetti complex? One of those complexes has a particular structure for these groups. Anyway, so de Horn and Goodell proved this result F sharp for spherical type groups, and therefore it held for the FC groups. And then we can deduce it for R groups, and therefore it holds for all groups because it's something that's closed under these amalgamated products. I think it therefore holds for any Artin group that you can build out of R groups and their groups using these amalgamated free products. But that doesn't prove it holds for all Artin groups. So we need essentially some kind of rewrite system in order to derive this property. So we can only derive it using our rewrite systems. I don't think we know how to derive it in any other way. But this is, I talked to Edin about this just over a year ago, and we've not written it down yet because other things have got in the way. But his work with de Horn, which proves it for the spherical type groups, is certainly written up. And I don't see any, we proved it, we just haven't written it down yet. So yeah, it seems to be a form of hyperbolicity. But we know these groups aren't hyperbolic. They just have a lot of properties that hyperbolic groups have. Like they have nice rewrite systems, and they're automatic. All of these groups are automatic. All of the groups that we consider, and all the spherical type groups. Oh, except the spherical type groups aren't short lex automatic, of course, or aren't known to be. They're just known to be automatic. So our groups are the only ones that are known to be short lex automatic, which is kind of interesting. I'm sorry, I really ran out of time, so I haven't explained any of our details. But really, this is all done because we understand the normal form. Probably none of the rest of you do, which is our great advantage. because I blurred over the details too much. So we claim we have this nice normal form, but we're not explaining it to any of you, so we can carry on using it and we're one step ahead of you all the time. Yeah, so. I just wonder who's sitting there. Sorry, I'm trying to suss out who's there, because the camera isn't very good. I can't see who everybody is. I can see Murray and I can see Laura. I can't see who the guy in the red t-shirt is.
Yeah, I'm one of my students.
All right, and I can't see who the guy in the blue shirt is. It's probably somebody I know, but I don't know who he is. But, yeah.
That's Colin Rees. And Volker Dika is here.
Now, I know Volker was here earlier, but I can't see him at the moment. He's out of sight. Maybe he's... Oh yeah, you're behind Laura. I thought you disappeared to get a cup of coffee.
Camera's right.
And then Cameron Rogers, the student here, and George Ellis.
Oh, George is here.
Yeah, yeah.
Oh, hi. I'm sorry, I couldn't... Which is
We
his...
should have introduced ourselves.
It's not in the picture. I know you are.
Yeah, I'm sorry, because I was reserving BAMCon especially for George, and I thought he wasn't there, so I thought I'd only talk about this. But, yeah.
Thank you.
So I haven't given you any of the detail, George, I'm sorry. I thought you would understand it. But, still. Anyway. Hi.
Okay, thank you very much again.
Thank you.